All right, everybody, welcome back. We will go ahead and wrap up our discussion of ODEs. Just as a reminder where we are in the class, too, today will be the last day that we do anything that feels like new material for CENG 15. This will pretty much wrap it up. The plan for Friday is to post the midterm a little bit before class and then use the first not the midterm, post the final a little bit before class and then use maybe the first like 10 or 15 minutes to go over it. But the rest of the time will be mostly just like an office hours. So you can either come here and work on it, you can stick around wherever you are and work on it. I'll be in Canvas chat if you're on Twitch and want to ask questions during that period. But there's not going to be any content or anything like that on Friday other than to just review the final for the first few minutes and then have kind of an open office hours after that. What we're going to do today is do a couple of examples of ODEs and then build ourselves up to solving systems of ODEs. I do want to make one comment too. I have an appointment right after class, so I'm not going to be able to stick around either here in person or in Canvas chat after class. So I'll have to kind of end it rather sharply right around 3:50, just as a heads up. So let's switch over to Matlab. We'll solve a couple of ODEs. The thing that we're going to focus on for about the first 30 minutes or so is how to manipulate the output. So the solution's the same pretty much all the time, but often we want to do something to the output. And because it's a bunch of numbers that are supposed to approximate a function, there are different ways that we can tell it which numbers we want it to output. Unlike F0 or Fsolve, where it's just, there's only one number that pops out, right? One for each variable or something like that. So there's not a lot we could do with that. For ODEs, you can play around with the outputs a little bit more. So let's look at an example over here. I pulled this example from an old homework. Don't worry, it's not on your homework. We won't have to do that. But what you're looking at here is a horizontal tank, which is cylindrical. It's a very common shape for a tank. It's very mechanically sound. It's easy to make. And of course, it acts like a natural drain, so you don't have dead spots inside of there. And there's a pump underneath it, and it's draining out the tank at a particular rate, Q, which is constant. The height of liquid inside of that tank is a fairly complicated expression. It's not impossible, but it's a little bit of a mess to see it in analytical form. But written as an ordinary differential equation, it's fairly compact. So if you wanted the analytic expression, you'd have to integrate this ODE with respect to h, which is, I mean, it's in the denominator, it's under a square root, and there's two of them, so one of them is going to be squared on its own. Like, I bet you could do it, but I personally don't want to. But in ordinary differential equation form, that's not too bad. We can type that in pretty quickly. So what we're going to do is write that differential equation and then solve it for a couple of different conditions that are here to give us the liquid height as a function of time. And then we're going to use that solution to look at different ways we can manipulate the outputs from ODE 4.5. So remember, the first couple of steps in solving a differential equation is A, recognize that you have it, which this is, and that it's in its correct form for use with ODE 4.5, which is the differentials on the left and everything else is on the right. Usually they're already written that way, which this one is, so we don't have to do any rearranging there. You should identify the initial condition. So if you read through 6.3a here a little bit, actually it's not until 6.3b, it says the initial height in the liquid is 3/4 of whatever the diameter of the tank is. So that'll be our initial condition. A couple other things, we know what Q is, we know the diameter is 1 meter and the length is 5, so we know those parameters inside of there. We also need to know the range over which we want to evaluate this differential. And that's given in the first line of 6.3b. It says solve it from t is equal to 0 to t is equal to 630. So that'll be the range that we end up solving. And then 6.3c, I've added that here so that we can illustrate something else. We'll come to that after we solve it the first time, which is determine the height of the liquid in the tank at exactly 411 seconds. So we'll come back to that. Oh, there's a couple of notes here that we will delete. because we'll come back to those here in a moment. So let's set this thing up. The first thing that we need is that initial condition. So h0 is our initial height, and it's equal to 0.75 times the diameter, whatever the diameter happens to be, just so that we can see that it's not always just a number, right? You can calculate that based off of other things. We'll adjust it so that we define the diameter as 1 meter and the height as 3/4 of that. We need our time range. That is our 0 to 630, and it's in seconds. And then when we go to solve this, the call to ODE 45, it's going to give us two elements as output. And we're going to call ODE 45 with that syntax that looks very similar to, actually, we'll call it ODE tank, since that's what the question asked us to do. It looks very similar to like an fsolve kind of syntax with this extra input argument, which is our interval of integration. So this is our time range. And then our initial condition is just h0. It starts off at 3/4 of d. Remember, that's not a guess. h0 is not like, I think the function looks like this, or I think the answer is here. It's saying, I know the value of that function at a particular point, and this is what it is. It's at that initial condition. The things it's going to output are t and h, but they're going to be as vectors. So they're going to both be column vectors. So we can expect this to be t and h. Just to keep us sort of a little bit more clear about exactly what's coming out, it's a little weird to have like t and h over here and t and h over here and t and h over here. Like, what is the difference between all of those? I'm going to call these two tsol and hsol, just as a reminder to us that those are the solutions. That's our function that's coming out. Or I should say, it's our vectors of data which represent the function that is the solution. And then the question is asking us to plot those, so we'll plot tsol and hsol as a black line. And of course, always get into the habit of labeling your axes. I believe the units on h here are meters. And now we need our local function. So we were already told the syntax up there is function dh dt is ODE tank of th. And this one, it's pretty much given to us. We don't have to do too much in terms of manipulating this. I'm just going to take a little screenshot of this and move it down so that I can write it down here. So there's the function we're trying to write. You can use the sandwich method when you're constructing this local function the same way that we could with f0 and fsolve. Usually when there's only one differential equation, there's nothing you need to do for a top bun. The top bun is essentially already the input that sits in here. But you can give yourself some space and write the bottom bun as your differential. So dh dt is equal to all of that stuff on the left. So minus q divided by a quantity of 2 times L times the square root of h times d minus h. So this is our bottom bun. If we're doing top bun, bottom bun, I guess we could add on here, no need for a top bun, since t and h are inputs. Once this function gets started, as soon as it enters this function workspace on line 9, the only thing that it knows are t and h. So by the time it gets down to line 11, it needs to know what's q, what's l, and what's d. So we have to define all of those along here. If we had read that problem statement through a few more times, which I'm not going to do right now, we would see that q is 0.005 cubic meters per second, d is 1 meter, and l is 5 meters. So we can define constants and stuff like that. Of course, you could always just take those and pile them inside of your expression. But again, for me, for troubleshooting and debugging, it's a lot easier for me to read this expression and compare it to this one rather than try to do the substitution in my head and remember like, oh yeah, 0.005 is q and sort of line those up every single time. I sort of spread those apart so I can limit the amount that I have to debug on any particular step. So I'll delete that. Let me just double check. It was 2 zeros. Matlab will usually complain because so often we don't need both of the input arguments on our ODE function. It'll highlight it in orange and say, I think you haven't used this. You've defined it, but you haven't used it. You might want to omit it. Don't omit it. ODE 4.5 needs it there to know which variable is which. It always follows this pattern of the thing on the bottom followed by the thing on the top, which is independent variable followed by dependent variable. So if we run this, we should get our plot. Let me turn on my function key here and run this. Otherwise, we'll do some debugging and see what happens. Yeah, so that's pretty much the plot that we're interested in. The height in the tank kind of goes down almost linearly for a while. That's sort of in the wide spot of the tank where the curvature is kind of less important. And then as it gets lower and lower and lower, it starts to accelerate because the curvature is starting to change a little bit. Notice it looks like it's going down to 0 pretty fast shortly after 600, right? It's kind of taken a turn for the worse there. What would happen if we extended it? Instead of going to 630, if we went to 700, what will happen kind of depends on exactly what your function is. Right away, we get a warning that unless you're a physicist or an electrical engineer should worry you, which is there are imaginary parts to your answer. Physicists and electrical engineers actually have functions that have imaginary parts, but mechanical engineers and nano engineers rarely do. Well, maybe nano a little bit more, because depending on where you go in quantum mechanics, they use imaginary ones. At any rate, we're trying to plot something which should not have imaginary components. If we look at the plot, it made this sort of weird-looking bend when it hit 0. In fact, we could add a little line that goes through there just to illustrate that it happens to be right there at that bend. So you can see right as it hits 0, it was able to keep plotting. But what's happening after 0 is that the h is negative in that square root. And so it's plotting the real part of a complex number, which is basically meaningless to us. And so it's one of those things that you have to keep in mind. The computer will spit out a number, but you have to recognize that that number is crap. It doesn't mean anything, right? We've drained the tank. There's nothing else that we can do. So there's no point in going too much beyond where that exact point is. The most that you could try to do with it is, you could try to do like a root finding operation here and say exactly how long does it take to drain the tank, and you would run this until it hits 0 and estimate it from something like that. But let's keep it at 630 just so that we don't have to worry about that imaginary part. We don't get those errors coming out. We don't technically need that Y line anymore. But it's just a reminder that the computer doesn't know better than you do, and often it will output data even if they are meaningless, just because it's able to do it. So I'll pause for a moment here. We're going to mess around with the outputs on here, so I want to make sure that we all are starting from the same point. So we'll wait, 30 seconds, maybe a minute or something like that. We'll go up to 3:15, just in case you have any of this code you don't have, so that we can all be on the same page. I don't know if anybody saw that on Twitch, but just for a moment there, we had 3, 1, 4. Oh no, it would be 14159, wouldn't it? Not 1459. We had very close to pi on the clock right there. So this last part, 6.3c, determine the height of the liquid at the tank at exactly 411 seconds. What is that asking us to do? It's asking us to do something like an x line at exactly 411 seconds. We'll make it red. If we were to imagine drawing that vertical line on our plot, it's asking us where does that intersect the plot, right? Tell me what the value of h is at exactly 411. There are a couple of different ways that we can do something like this. So to get ODE 4.5, to output a value at a specific point can be done in a few different ways. The first one is sort of a, I don't know what I would call it. Let's call it the uncomfortable way, since I'm uncomfortable thinking about it. The uncomfortable way to do it is to set the t range to that value. Or I should say set the second element of t range to that value. So in other words, that means something like t range will be 0 to 411. Right, if I just come down here and replace this 630 and say 411 and run that, it'll just run it right up to 411, and there you go. You've got it right up to 411. The last element then of HSOL corresponds to 411 in time, I should say. The reason that I say that that makes me uncomfortable is it's kind of weird to just set the range arbitrarily like that. It's not wrong. The solution is no less or more accurate based on changing that range there from 411 out to like maybe 630 or something like that. But the endpoints are treated ever so slightly differently than the rest of the points. If we were to plot this as, say, dotted lines, or actually, how about circular lines so that we can see it? On this one, it's essentially the same. On fast-moving, or I should say ODEs that change very rapidly near the end or the beginning, the points tend to clump up around the end and the beginning in those cases, and you can get mild variations. So it's just a little bit weird to change sort of the range of the problem just to know the value in the middle. That's why I say it's a little bit uncomfortable. The other way to do it, and the way that I generally recommend that you do it, is to replace the output with a single variable, and this variable will be called a solution object, which is a name that Matlab uses for a number of different things within its built-in functions, but solution object is one of them. It comes up in calculus and it comes up in statistics a lot inside of the functions that Matlab has for those two topics. So you replace the output with a single variable. It's called the solution object. Then use a function called deval to evaluate the solution at the desired point. So let's put this as like the recommended way. I only say recommended because it sits better with me. There's nothing wrong with changing the t range. It's just kind of inelegant. So if we imagine taking this and copy pasting it, right, that is our full command to ODE. Let's comment out, actually, let's just leave the first one since we're going to use it anyway. Instead of tsol and hsol, we can ask it for a solution object. I call it sol obj to remind myself that this is a solution object, but you can call it anything you want. You can call it A if you want. That's perfectly fine. The old plot still works the same, right? We can still call it from tsol and hsol. If we wanted to evaluate the solution object, let's move our plotting commands down a little bit. How would we do something like that? The thing that we're after is h at 411, so I'll call it h411. We use this deval function, and we pass to it the solution object and the point at which we would like to evaluate that solution. So we would like to evaluate that at 411. So this evals the solution at t is equal to 411. So if we were to add these on here, let's add another line. We could add a y line, this time at h411, and we'll make this one blue dashed so it stands out. So the intersection of these two should be right where that plot intersects x is equal to 411, or in this case, t is equal to 411. Oops, I forgot to increase my range. So 630, I believe, was where it was before. So if you change those two, now you can see the intersection of those two lines is pretty much right where we expected it to be. As hopefully that would do, the d-eval function has said this curve can be represented as a solution object, which you can kind of mentally keep a picture of, like that's as close to an actual function as you're going to get. It just can't be evaluated like a normal function. You have to use this d-eval to evaluate it. But it landed right where we wanted to, right at the intersection of those two plots. The d-eval function can also accept a vector of points. So let's say you didn't want to call ODE 45 twice, right? We called it once here and again over here. If you didn't want to do that, you could do everything with just the solution object and then evaluate the solution object at lots of different points. So instead of this, we could say tsol is, I don't know, Linspace from 0 to 630. And then hsol is d-eval of the solution object. And now instead of giving it a single point, you can pass an entire vector to it. And that is entirely equivalent. Well, not entirely equivalent. It is very nearly equivalent to the ODE 45 call. We'll get into exactly how it's a little bit different in a second. But if you run that, you'll get the same looking plot. Again, none of these changes have changed the actual solution, the way that Matlab interprets the solution. ODE 45 has gone through exactly the same steps every time, and it has produced for it the same answer. The difference is, how did we ask it to tell us what that answer is? Originally, we said, well, just give us the vectors t and h, and we'll plot them. And then when we replaced that with a solution object, we said, well, bundle all that information into something and let us evaluate it somewhere else. And that's what we've got with the d-eval function on there. Those would be the points to keep in mind, right? In case you don't come across ODE 45 for a number of years, I wouldn't expect you to remember the syntax. What I would hope that you would remember is you don't change the way it solves, but you can ask for different kinds of outputs. And that might be enough for you to dig through the documentation and find out what do those look like. Because I know I can get it to evaluate it as a single point or a vector or something like that. That's what we're after. So I'll just pause for a moment here. We're going to go on to another example in just a second. So I'll leave this up in case there are any questions or anybody's got to keep up with the code. I'll add a comment there because when I post this, I don't want you to think there's something wrong with that line 4 that we commented out. Nothing wrong with line 4. It works fine. Okay, well, that was something. All right, let's look at another example here. That finishes our tank example. A couple of different ways that we can change the output. We just did that with d-eval. So the default behavior, if you didn't notice it over in the workspace, is you just get a vector of outputs, and they have a different number of elements each time. Usually it's somewhere on the order of 50 to 100. If you had checked the No, that's great. If you had checked the actual length of the ones that we had before, they would have been 49 elements, which is pretty close to 50. There are two ways that we can modify the outputs. One is what you just did, so I don't know if you need to write this down all over again, but you use d-eval with a solution object. So that's one way to adjust the output that we have. This is the second way that I want to talk about here, which is instead of providing the input as 2 elements, you can provide it as a vector of many elements. And that's something that we haven't seen previously. If you do that, then the output will be provided at exactly those points and only those points that you asked it to. But importantly, it doesn't change the accuracy at all. So this part I would add, even if you only ask it for like 4 data points or something like that across the entire range, it is every bit as accurate as if you let it do its own thing, or if you ask it to do that at 1,000 points. I shouldn't even say there's no loss of accuracy. There's no change in accuracy. Certainly there is no loss, but there is definitely no gain either. So if you ask it to evaluate it at 1,000,000 points, that's no more accurate than if you had asked it to evaluate it at 3 points. Because it's not changing the way the underlying code is being solved or being evaluated, it's only changing the output. It's only changing the way that we see the result. So I've got 2 what are called parametric equations down here that I'm going to give you probably, let's go about, I don't know, 5 minutes. We'll come back at 3:21. Or, no, sorry, 3:31. See how much of these you can get coded up. They are separate equations, so you'll have to call ODE 45 twice, once for the first expression and once for the second expression. But the initial conditions are there, and I'm asking to have them plotted over 0 to 2 pi. And if you try to plot z as a function of w, most likely you will get an error. If you get an error for that, you've reached where I want you to be, and we'll address that error when we come back. So take a few minutes and see if you can code up a fair amount of this. All right, I'm going to start with the local functions first, and I'm only going to write one of them. So let's write that first one, which is dw dt, and we need a name for it, unicorns, of t and w. This is one of those cases where it is a little bit annoying to come up with function names, because those functions don't really mean anything, right? They're just representing an equation that's there. So the name of that ODE really doesn't matter. We don't need much of a sandwich structure here because dw dt can be written all in one line. So minus sine of t minus the square root of 2 times the cosine of t times the sine of t. The reason I said I'm only going to write one of those is because whenever you find yourself writing a single line like that, and that encompasses everything, it's not a bad candidate, or I should say in another way, it's a pretty good candidate for a local or for an anonymous function. So I'm going to leave these here, but I'm going to comment them out. It is possible to use ODE 4.5 with local functions in the same way that you can use F0 with local functions. That's perfectly fine. So just to practice the local function syntax, we'll define dw dt as a function of t and w, and it's minus sine of t minus the square root of 2 times cosine of t times the sine of t. So this sort of reads a little bit more naturally, right? We don't have the word unicorn floating around for no reason. It's pretty clear that it's a math function, and it's a function of t and w, and we just happen to call it dw dt, but we can still read it pretty clearly off of the assignment. So it's a good candidate for an anonymous function. Similarly, dz dt is this time a function of t and z, but it's going to be cosine of t squared minus sine of t squared. Remember, anonymous functions get defined before you use them. Local functions get defined all the way at the bottom of the script. And that's just syntax. There's no special reason for that other than that's the way Matlab needs it to be. We can define our initial conditions, so W0 is 0 and Z0 is 0. And our t-span is going to be 0 to 2 times pi. Why 2 pi? Because it asked us to do 2 pi. Now we can solve both of these, and we'll get something like t-sol, and the first one will give us w-sol, and that'll be ODE 4.5. When you use an anonymous function, you can put that wrapper around there like we did before. So it would be okay if you wanted to do at tw and then dw dt of tw, but it's just sort of redundant because it already knows it as a function handle. So you don't have to do that sort of double definition of a function handle when you've defined it as an anonymous function. So you can just say solve dw dt. Which again, anonymous functions kind of make this look a little bit more readable, right? Because now it's pretty clear you're solving dw dt. Enter our t-span and enter our initial condition, which is w0. And then we'll do this again for z. ODE 4.5, we're going to solve dz dt for the same t-span, but with a different initial condition. So Matlab has sort of highlighted for us. You can see it's in orange here. It thinks there's something wrong with t-sol. So if I hover on top of t-sol, it says it appears to be unused. Although we have used it, the thing that Matlab is trying to tell us is that we define it in line 6, and then we overwrite it in line 7. So like, why did you define it in 6 if you just replace it in 7? And we really shouldn't call it the same thing because the points associated with the w solution are not necessarily the same as the points associated with the z solution. So I'm going to call these t-sol for w and t-sol for z. And actually, I'll put an underscore on there just so that that doesn't look like a, I don't know, weird combination of letters that sit on there. I'm also going to clear my workspace just so that we don't have to look at anything else right now. We're not going to do the plot just yet. In fact, well, let's do the plot. If we wanted to plot z as a function of w, we would say plot w sol here and z sol here. And we'll just make it red. If I try to plot that, I get an error. It says the vectors have to be of the same length. This gets back to that idea of ODE45 is generating some output vectors, but you can't control how long they are by default. If you just tell it, give me some values from 0 to 2 pi, it found out that in order to solve dw dt, if you look over in your workspace, it needed 41 elements for that. So if you look at your W sol, it's a 41 by 1. Similarly, T sol for W is also 41 by 1, right? Those have the same amount of elements in them. But when it went in and tried to solve Z, it needed to do a few more evaluations. And so we ended up with a 61 element instead of a 41 element. And so we can't plot those against each other because one has 41 elements and one has 61. There's nothing wrong with that. That's the default behavior of ODE45. This second point that we had up here, instead of providing the range as 2 elements, we can provide it as a vector of many elements. We know a couple of different ways to make vectors of many elements. One of them is Linspace. So instead of 0 to 2 pi for t-span, if we say Linspace of 0, 2 pi, now we would expect 100 elements, right? Because the default behavior of Linspace is 100 elements. The way ODE45 will interpret that is it will look at the vector of 100 elements produced by Linspace, and it'll say, I interpret this as start at the first element of that, which is 0, and go to the last element. And ODE45 will run away, do its solution over that range. Then it'll come back and say, you actually asked me for more than just those 2 points, so I'm going to provide you an output evaluated at exactly the points that you asked me to do, which in this case is 100 of them. So now if I run that, all of those will have exactly 100 elements, and I'll be able to plot it. And I'll get a little fish if I plot that. And if you wanted to, if you said hold on, and then you say plot, let's go around, what is that, minus 0.5 and maybe 0.25? You could add a little eyeball on there too. So now you've got a little fish with an eyeball on it. Never let it be said that Matlab does not have practical uses. But again, keep in mind, the Linspace by default should have been giving us 100 elements. And sure enough, if you look over in the workspace, the T-sols for W and Z have 100, as do the W-sol and the Z-sol. They all have 100. If you change the way that T-span was defined with Linspace, maybe instead of that you wanted, I don't know, 27 points on there. It would give you that with 27 points, and your fish would get a little bit more blocky, right? Because it's not evaluated at quite as many points. But the underlying solution that ODE45 calculated is no different whatsoever. It has the same accuracy. It's just you didn't ask it to evaluate at so many points. You could ask it as few as like 3. And it would still do it. Your plot just looks terrible, right? Because you're trying to plot a fish with 3 points. Maybe 5, you can see it. No, I can't see it with there. How about 10? 10, you're starting to see a little bit of a fish, right? But again, ODE45 is solving exactly the same problem every time. It's just evaluating it at a different number of points. Excuse me. So let's set that back up to a reasonable number. How about, I don't know, 75 points. 75 gives a pretty smooth-looking fish on there. So this is all about manipulating the output. Just keep in mind it doesn't do anything to the solution itself. This kind of system of ODEs is, it has a name for it, but we don't use it very often because it's kind of the default. We assume that ODEs look like this. These are what are called not coupled or uncoupled ODEs. When we went to solve these two, when we wanted to solve dw dt, we just called it all by itself, right? We didn't need to know the solution to dz dt, we just solved it. And similarly, when we went to solve dz dt, we could have done that in the other order or without dw dt, it would have been fine. It is nonetheless a system of differential equations because we're kind of solving them together. But there's another class of differential equations that are what we call coupled, where the answer to one relies on the answer to the other and vice versa. So you have to truly solve them at the same time. in an analogous way as the way when we went from F0 with one equation to Fsolve with multiple equations, there's no way that you can sort of subdivide the steps of Fsolve and kind of solve one at a time. You got to solve them all simultaneously and figure out what the answer is. A significant number of differential equations have that problem. We're not going to go too deep into this beyond just setting up the syntax. It does follow very similarly the syntax for Fsolve, but the reason I don't go too much into detail is if you're not a chemical engineer, it probably won't come up. If you are a chemical engineer, we review it in the class where you need it. So I'm just introducing you to the syntax here. That syntax, I'm going to switch over to the book for 113, because it's got the syntax already in it. Suppose you have these two differential equations. These are what are called coupled. And earlier this morning, I found out I have a typo in here. It's dx dt is z plus 4. This one is supposed to be dz dt is equal to minus 3x. And the point I want you to notice is the z that is on the right-hand side up here, that is the dependent variable in the second expression. And the x that's down here is the dependent variable in the first expression. So there's a coupling here, right? The answer to z is required to know the answer to x, but then you get into that loop where the answer of x is needed for the answer of z. So you have to solve them both what we call simultaneously. We call these coupled. The structure that we use for coupled ODEs is nearly identical to what we use for Fsolve, which is why we studied Fsolve in the first place, other than it's got its own uses. So what we end up doing is bundling them into this y vector. And you can see all of my typos that I found this morning because I thought it was y instead of z. We think of it as, again, a column vector, this time of independent variable or dependent variables x and z. We give it a column vector of our initial conditions, and we bundle our differential equations as another column vector. So this has a very similar pattern to what we did with Fsolve. And in fact, Matlab tends to use the same default variable for it, which is this sort of capital Y. I don't know why Matlab chose to use capital Y for everything, but we do it to be consistent with Matlab. So as an example, let's solve this particular set of equations really quick. We will set this up. So I'll move this over to Matlab. We'll give ourselves a new script over here. It's a little bit big. And I have to remember what the initial conditions are, so I got to grab those. I defined those in an example a little bit further down. There it is. And I'll make this a little bit smaller. So here's our system of equations. Again, there's a typo in there. It should be dz dt for that one. And we need to solve that from 0 to 5, subject to those two initial conditions on there, and then plot it. So the syntax for this, we start bundling things in the same way that we did for Fsolve. So we think of y as though it is a bundle of x and z, right? That's the pattern that we're going to use. So when we want our initial conditions, we would call those y0, and we would put the initial condition for x, which is 1, and then for 0, which is 0, or for z, which is 0. So this looks like x0 and z0. In a way, entirely analogous to the way that we would guess the solutions for Fsolve. Just remember, when you're solving ODEs, it's not a guess. You're saying, I know what the answer is at that particular point. The output, we're going to get t's and y's from ODE 4.5, and it's going to be solving something. We'll call it the ODE function of t and y. We need to give it its t-span again, as well as its initial condition. The t-span doesn't actually change, so t-span here is still 0 to 5. This is unchanged. I'm just going to display y for now, and we will look at its structure. But now we have to define the local function. So we're going to be calculating dy dt, and it'll be for our ODE function of t and y. This one, because there's more than one variable, using the sandwich structure is not bad, so we can give ourselves a top bun and a bottom bun. The first element of y is x, and the second element is z. So here's our top bun. And then our bottom bun follows the same kind of structure that fsolve did. So it's kind of convenient that they both follow that same structure because it's a little bit less syntax to remember. Our first one is dx dt, which is, well, we can write it out. We can say dx dt is equal to whatever that function is that we had up there, z plus 4. And dz dt is whatever our other one is, which is minus 3x. But then we have to bundle those into dy dt. So the dy dt becomes dx dt followed by dz dt, which you could write directly if you wanted to. That would be fine. Or you could write it as we did before, where it's like dy dt of 1, comma 1 and of 2, comma 1. Any of those would work. But here's our bottom bun. And then if necessary, we would fill in anything in between the two. So if I look at these two expressions, I need a z and I need an x. Everything else is defined, and I happen to already get the x and the z from the top bun, so there's nothing else that I need to define inside of here. Oops, there's a little typo there. That needs to be lowercase dt. So if we run this and look at what y looks like as a solution, we see that y looks like a matrix. It's got a lot of rows and 2 columns. Those 2 columns are coming out in this sort of a pattern. They're slightly reversed, but it's essentially this pattern. Y is coming out with the first column as x and the second column as z. So we can extract those elements out. If we wanted to say, for example, xsol, let me clear this in case you were writing code down there. The solution for x is the first column of y. So we can say, give me all of the rows of y and the first column, and zsol is the second set of columns. And now if we wanted to plot that, let's change t. Instead of t, we'll call it tsol. We can now say plot tsol xsol, and maybe that one will be blue. And then hold on, and then plot the other stuff, tsol and zsol, and maybe that'll be red. Again, we should get into the habit of always labeling stuff, so we'll label things as best we know them. If we have 2 curves, it's a good idea to put legends on there, so we'll add a legend of x and z. And we should get a plot that looks something like that. I'll make my plot a little bit smaller just so that you can see all of the code that's on here. So it shares a similar quality as fsolve in the sense that we bundle things as this sort of super variable y, and we're expecting things as column vectors everywhere. The result is admittedly a little bit weird just because of how it flips it. I would have expected them to be row vectors, but they end up as column vectors, but that's okay. But this is an example of solving a system of coupled differential equations. The nice thing about ODE 4.5 is you don't have to switch functions. So when we wanted to solve one equation, we used f0. When we wanted to solve more than one, we used fsolve. With ODE 4.5, it's the same function for both. You don't have to come up with another function. It can handle a single ODE just as well as it can handle a system of coupled ODEs. It's fine. It doesn't care one way or the other. Which I suppose you could go the other way. fsolve can do one equation too. That's fine. Whoops. Didn't mean that. So I am going to wrap it up here. Like I said, I have that appointment afterwards, so I need to be stepping right along, and it is 3:50, of course. So our plan for Friday is in the first few minutes, probably 10 minutes or so, I'll describe what's happening in the final. It'll be posted before that, so you'll have access to it. And then after that, it'll be kind of like an office hours. You can stick around if you want and work on it. I'll be in Canvas chat during that time as well as on Twitch, so you can ask me questions on Canvas chat and maybe I'll just respond on Twitch. Other than that, we are all set with CENG 15. There's no more content that we're going to be covering, so thanks for bearing with me the whole time. I'm sure it will come up sooner or later. Hopefully, you'll walk away from this class with what I would like is if you have a good enough idea to say, I remember I did that and I remember roughly how to do it, you're in good shape. I don't expect you to remember like, oh yeah, ODE functions with deval and all that. But if you remember like, yeah, it can solve it and I can change the output, that's in pretty good shape. Because that's enough for like a strong Google effort or a strong Bing effort to remember what the actual syntax was. And I think with that sort of knowledge coming away from this class, you'll be pretty well prepared for most of the other stuff. Because most of the time your instructors will review exactly the syntax that you need, and it'll feel more and more familiar as you go. So we'll wrap it up there. I will see you back here on Friday if you can make it. If not, I understand, because we're only going to be talking for about 10 minutes. But otherwise, good luck on your other finals, and I will hopefully see you in another class. So bye, Twitch. I'm going to wrap it up.